In this paper, we're going to talk about the design and the study of a fully soft switch high-step up DC-DC converter with dynamic band graph modeling and PID controller using a state space averaging technique. I am Sayed Arashomidi and I'm going to present this paper as a project of instrumentation and control of energy system course submitted to Dr. Mohsen Jamil. Here we have the proposed converter, which is a combination of choke converter and boost converter using shared component technique. Here we have a boost converter. It's a conventional boost converter. Here we change the place of the inductor and diode. Functionality is still same. Here we have the upside down of the previous part. And as you can see here now, the input voltage of the boost converter is negative, similar to here the voltage across the S2, which is negative, and because of that we can use these two inductors as a shared component and combine these and attach and combine these two converters, and then we have this uh, proposed converter. The conversion ratio of this converter is high. We can use it as a for highest of up applications such as PV systems. Efficiency is so high because of lack of any switching loss in this converter, which will be discussed in future. Reliable and compact. The reason is because of the strategy that we used and we choose to design this converter. The inductors are small, and also because of lack of any switching loss, we can increase the frequency, and again we can reduce the size of the passive components as well. Here we have the operation modes. This converter operates as 6 different operation modes, but first we need to know about the components that we use in this converter. There are 3 switches in this converter, 1 diode, 2 main capacitors, 3 snubber capacitors, and 1 inductor. At mode 1 we have this converter. The S1 and S3 are on, S2 is off, and the power transfer from input to inductor stores in this inductor, and power and energy from blocking capacitor transfers to output current. And here the S2 will be off at this mode, which is so short. At the end of this mode, S1 and S1 and S3 turns off, and because of the current of LO, it can discharge the S2 snubber capacitor, and after that in mode 3 we can turn the S2 on under ZVS condition, and now the stored energy in Li will go to blocking capacitor, and the stored energy in Lo will goes to output capacitor and load. And here because of the output voltage, in the current of the output inductor, the direction of the current of the output inductor will change, and it starts to discharge the snubber capacitor. In other words, the energy stored in a snubber capacitor of this switch will transfer to LO inductor, and at this mode S3 reverse diode is on, and at the end of this mode the S2 turns off under ZVS condition, and here all switches are off, and here the current of output inductor is much higher than input inductor current, and because of that the current can discharge the S1 snubber capacitor and charge S2 snubber capacitor, and because of that it will provide soft switching condition for S1, and we can turn the S1 and S3 under ZVS condition on. Here we have the equations. The conversion ratio is this: minus D over 1 minus D, 1 minus D minus D prime. Voltage stress across the switches and diodes are as following. Component design. The L1 is similar to boost converter. CU is a little different. It's D plus D prime over R times output voltage repole over output voltage times switching frequency. And here we have this formula which obtained by applying the principle of conservation energy on the stubber capacitors and LO and LI to be able to know the maximum amount, maximum value of LO. By knowing this amounts, we can design LO in a way to be sure that the soft switching condition will be provided for uh, S1 turn on and S2 turn off. Here we have the simulation results. We use C3M00 15065D as the power switch and 80EBU02 as the diode, power diode. This simulation done on output power 225 watts and input voltage 24 volts, output voltage minus 150 and 100 kilohertz switching frequency. As you can see here for S1 voltage and currents, you can see that soft switching condition is totally provided for both turn on and turn off situations. And for S2 as well, here the turn off the ZVS condition, and here turn on ZVS condition again. And here for the S3 as well, here we have turn on and turn off ZVS condition. Here we have the diode, it turns off under ZCS condition, which means for all semiconductors components we have soft switching condition, and the switching loss is totally zero. Here we have the voltage across the input inductor, here we have the voltage across the output inductor, and here we have the input and output inductor currents. As you can see here, the difference that we talked about, difference between LIO and LO current and LI current is observable here. Here we have the output voltage, which is the minus 150, and input voltage is 24. Efficiency analysis. Based on the sequence of from highest to lowest power loss, first we have semiconductors conduction loss, and then we have inductors conduction loss caused by ESR, and then we have capacitors conduction loss caused by ESR as well. So the reason is there is no switching frequency here, and because of that the major power loss is because of the semiconductors conduction loss. And as you can see here, diode and then S1, S2 and S3 are the majority power losses of this converter, and then inductors loss and then capacitors loss. And here we have the efficiency as a function of output power. As you can see, in a specific range, when we increase the output power, the efficiency will increase. The reason is in this range, the major part of the power loss is still same, and that means most of these power losses are not a function, are not dependent on the output current. They are dependent and function are they are dependent of the input voltage and output voltage. That means by increasing the output current and keeping the voltage same, the power loss won't change, and because of that the efficiency will increase. Here we have the band graph modeling of this DC-DC converter. The purpose of this modeling is studying the dynamic behavior of proposed converter. To drive all semiconductors, parameters, and parasitic components, we use the datasheet documents Yes, we use datasheet documents. As you can see here, the values have been obtained from datasheets, and here we have three switches: S1 here, S2 here, and S3 here. And here we have the diode, output diode here, inductor, output inductor, blocking capacitor, and input inductor. As you can see here, we have the parasitic gate resistor of the S1. Here we have the gate capacitor, and here we have the drain capacitor and parallel parasitic resistor of the switch, same as other switches. And here we have the parallel parasitic capacitor of the diode, and this resistor which illustrates the leakage inductor of the diode as well. Here we have the simulation results of this bond graph modeling. As you can see here, the details of harmonics are really great. The output voltage is minus 150 while the input voltage is 24. Here we have the output currents. Here we have the S1, S2 drain source voltages, and here we have S3 drain source voltage. At the other part of this article, we have the state space averaging technique and PID controller. We used a state space averaging technique to design a PID controller. By applying a state space averaging technique on small signal analysis, we can obtain A, B, and C matrices. Using following formula to calculate transfer function, as we know that we can use this one in a small signal analysis to calculate and obtain the transfer function. Since using these parameters and variables will take much space, we prefer to use the values which we use in simulation to calculate the transfer function of the converter. And here we have the transfer function of this converter based on the values that we used here in the simulation. Here in the simulation we used, and then we have the transfer function of that specific design. Here we have this schematic of the PID controller, output voltage, reference voltage, we have the PID controller, and then here we have the PWM generator to drive the power switches. And we use a CISO tool to design the PID controller. Here, as you can see, this is the body diagram of the closed loop purpose converter, and here you have the root locus of the purpose converter. By using this technique, trying to stabilize the converter and designing the PID controller, we have the function here, we have the transfer function of the PID controller, which designed and obtained by using the CISO tool in MATLAB. As you can see here, the gain margin and phase margin are acceptable in acceptable range, and that means it's okay. So here we have the simulation result of the Simulink model. Here we have the Simulink model of the converter, and here at the 0.1 second the output power increased significantly, and because of that we can see here a transient difference in the output voltage, and then again still stable. That means the controller works well. So in this paper we designed a novel simple idea for the highest step up DC-DC converter. We used a choke converter and a boost converter, and using a shared component technique, and after that we use a simulation to check the soft switching technique and the functionality and conversion ratio of the converter, and after that we designed a bond graph model to study the dynamic behavior of the converter, and we got the simulation results. And after that, we used state space averaging technique to design the PID controller and drive the transfer function of the converter. And after that, we used a CISO tool to drive the transfer function of the PID controller, and we used Simulink to design to model the closed loop proposed converter and got the result which was acceptable.